So this is Engineering Statistics and Linear Algebra 18 EC44 Module 1 Lecture 3. We are in the single random variables module where we will take it up now, discrete random variables and mixed random variables. Till now we considered about the continuous random variables. So a discrete random variable is a variable which can only take a countable number of values. Here the term which is very important is countable number of values. So countable is itself discrete. The variable is said to be random if the sum of the probabilities is 1. So there are two terms, discrete and random. Discrete means countable number of values, and if the variable is random if the sum of all the probabilities is equal to 1. So example is given over here. In this example, you can see that x can take xa, xb, and xc. For each of this, the probability is given here 0.24, 0.34, and 0.44. Right? Now, this can be considered as what is known as the probability, what you call distribution function, or generally we'll call this as a mass function, probability mass function, which is same thing as the probability density function, small f. Okay, so in the discrete case, the small f is known as probability mass function, or probability, you can call it as density function. It is similar to the density function, and it is known as the probability mass function. So between xa and xb, it will not have any value. Between xb and xc, it will not have any value. Only at xa it has 0.24, at xb it has 0.32, at xc it has 0.44. If you add all this, it will just become equal to 1. So this gives as an example of the discrete random variable with probability equal to 1. So this we generally write it something like this. The CDF for this can be written in the terms of unit step functions as 0.24 u of x minus xa plus 0.32 u of x minus xb plus 0.44 u of x minus xc. So what is this 0.24, 0.32 and 0.44? They are the probability values at x equal to xa, x equal to xb, and x equal to xc respectively, right? So 0.24, 0.32, 0.44 are value probabilities at xa, xb, and xc respectively. So the PDF can be written in terms of the unit impulse function, PDF or PMF as it is sometimes known as, is written as fxx is equal to, you just replace the u here by means of the del. You just replace the u here by means of the del. So u is unit step function, we know very well in signals and systems, and the what you call del, we know that it is unit impulse function. Impulse function looks like this, right? Step function will be a straight line, right? A straight line. So try to differentiate between a unit step function and unit, distribution, what you call impulse function. So this is impulse and this is step. Okay. So only difference is, they're just the same 0.24, same 0.32, same 0.44, same in both the capital Fx and small fx, only that here it is u, here it is del. Okay, that's the only difference. So now if you take that, now between the fxx, it's very straightforward. At x equal to xa it is 0.24, at x equal to xb it is 0.32, at x equal to xc it is 0.44. So this is very much straightforward, whereas this we need to try to understand this in the context of this. So when the value is less than xa itself in this equation, then u of x minus xa, u of x minus xb, u of x minus xc, all the three will be zeros, because xa, xb is greater than xa, xc is greater than xb. So if we are at a point which is less than xa, then u of x minus xa will be 0, u of x minus xb will be 0, u of x minus xc will be 0. Between xa and xb, we will have only this as 1, but these two will be zeros. So at that time, you will have the value of fxx equal to 0.24. So 0.24 between xa and xb. Between, what you call xb and xc, between xb and xc, because xb is greater than xa, this will be equal to 1, right? Because again, you know, the value, it is greater than xb, it is, this also will be equal to 1, whereas this will be equal to 0 because the x value will be less than xc. So this will be 0, only these two will be 1 in at the time when we are between x b and xc. So therefore 0.24 plus 0.32 will give us the value 0.56. For all the values x greater than xc, this, all the three things, u of x minus xa, u of x minus xb, and u of x minus xc will be equal to 1. So at that time, we'll have 0.24 plus 0.32 plus 0.44, and the total thing will be equal to 1. So that is why for all the values greater than xc, we'll have 1. So between xa and less than xa, it is 0. Between xa and xb, it is 0.24. Between xb and xc, it is sum of the two things, 0.24 plus 0.34. Above xc, it will be sum of all the three things here, 0.24, 0.32, and 0.44, and that is equal to 1. So that is how we will plot the fxx, the fxx. So generalizing for any, that is for an example, right? What we have considered there is just an example. But generalizing for any situation involving a finite number of discrete random variables, we can just write Sx is equal to xi for I equal to 1, 2, 3 till n. So Pi will be P of x equal to xi. Probability at x equal to xi will be represented by Pi. So when the range of observations Sx contain only discrete values, then x is the discrete random variables. Whenever we take the range of observations Sx contain only discrete values, might be I equal to 1, 2, 3, 4 till n, then capital X is known as the discrete random variable. This is another way of defining the discrete random variable. One way we have already, defined over here. So the probability Pi associated with the discrete random variable is called as the probability mass function. So we also call this as the probability mass function. So when all the discrete observations in Sx are considered, then probabilities must, according to the axiom 1, sum to 1. So if you add them up, whatever we have here, 0.24, 0.32, 0.44, some of them will be equal to 1. Right? The addition of them will be equal to 1. So for discrete random variables, fx of capital Fx, so this is the distribution function, right? Cumulative distribution function, fx of xi plus minus f of fx of xi. Both the terms are, xi here, plus and xi, that is equal to 0. Fx xi minus f of x xi minus over here. So here it is between plus and xi. Here it is between xi and xi minus. The value will be equal to pi, because at xi exactly that will be equal to the value pi. The CDF for a discrete random variable may be written as, so using this we can just write the, what you call, a closed form for capital Fxx, that is the cumulative distribution function as sigma of pi u of x minus xi, I equal to 1 to n. Okay, this is the closed form which we have already mentioned here also. So this is what we have mentioned, probability at each of that and at each of those points. Same thing is being mentioned here also. And then the PDF of the random variable is given by fxx, small fxx is equal to, this is the probability density function, or sometimes we can call it as mass function, but mass function might be associated with pi only. Using the mass function, you can write the probability density function. So pi of del x minus xi. This is impulse function. This is step function. Okay, try to differentiate between these two. So let us take another example over here. So what is given to us is this. The probability for a discrete random variable x is given over here. Fxx is pi value is given over here. This is the mass function. Then this is the, what you call, cumulative distribution function that will turn out to be the capital value fxx. Okay. So if you just see here, we have written here 0.05, 0.15, 0.22 and all that. Point one, the thing which should be remembered is if you add all of them, it should turn out to be 1. If you add all of this, it should turn out to be 1. Further, you know, the values which are there over here will be, if I want to find this, it will be sum of these two. If I want to find this, it will be sum of all these 3. If I want to find this, it is sum of all these 4. If I want to find this, it is sum of all these 5. If I want to find this, it is sum of all these values, right? So it should be very clear that the sum of all these is 1, and this value 0.64 is just nothing but 0.05 plus 0.15 plus 0.22 plus 0.22, and hence that will become 0.64. So these values plotted here gives us the fxx. These values pi is plotted here will give us the fxx, and these values plotted here will give us the capital fxx, that is the cumulative distribution function. So this is cumulative distribution function, and this is the probability density function. Okay, probability density function. So we also have what is known as the Bernoulli random experiment, which produces two mutually exclusive events, A and A bar. And the probability of these events, A and A bar, are denoted by P of A is equal to small p and P of A bar is equal to Q. And because we have only two events, then P of A plus P of A bar should be equal to 1, or nothing but small p plus small q should be equal to 1. So using the Bernoulli's probability model, a counting random variable x is assigned the integer either 1 and 0 as follows. So generally we will write xa is equal to 1 and xa bar is equal to 0. Xa is equal to 1 and xa bar equal to 0. So Sx will be the value 1 or 0. It can take either 1 or 0. Now consider a binomial trail of the order, that is n. We will consider the trail of order n. Here we have considered only one experiment, but here we are considering n number of experiments. So that is n independent Bernoulli trails, each with outcome a and a bar, s equal to a and a bar. Then the counting function will be equal to y equal to sigma of xi, I equal to 1 to n. Okay, whatever counting function will be there will be corresponding to the addition of all the xi's, all the n independent Bernoulli trails, n independent Bernoulli trails. So the counting function which corresponds to this will add a value of 1 to y each time the event A occurs. An event A contributes 0 to the sum in y. So we see that the event A contributes 0 to the sum in y. In this way, we count the event A in a binomial trail of order n. So probability mass function introduced with x in 2.31 will be P of x equal to 1 will be P, P of x equal to 0 will be Q. Sum of these two values will be P plus Q. And we generally write the PDF and the CDF like this. So again, whatever we have written earlier for small fx, that is PDF, we are writing Q into del x plus P into del x minus 1, right? Here we are taking the impulse function, whereas in the cumulative distribution function, we are taking here capital Fx equal to Q, the unit step function ux, and P, the unit step function which is x minus 1, because P is corresponding to x equal to 1 and Q is corresponding to x equal to 0. We try to write over here as Q into ux plus P into ux minus 1. For x equal to 1, we will have x minus 1 equal to 0, x minus 1 equal to 0. So because of that, this p will be multiplied by u of x minus 1. Similarly, when we talk about the counting function, when we use the counting function, then the PDF for the binomial trail of order n can be written as sigma of p and k del y minus k, sigma of P and K u y minus k. So again, unit impulse function, unit step function. For unit impulse function for PDF, unit step function for the CDF. Okay, that's the difference. This P and K is just same as the Pi itself. So where we can just write Pk as Pk or Pnk or Pi, whatever you call it, is equal to Pnk is equal to Ck. This will be straight away, the combination Cnk P to the power k Qn minus k, 0 less than k less than n. This is the binomial distribution. Okay, this is the binomial distribution or binomial random process, which comes out of n set of independent Bernoulli trails. N independent Bernoulli trails will give us the binomial distribution, random variable or binomial distribution. Okay, so using that, we can try to see an example of the same. So we have the table here, which whatever I have explained to you, same thing will turn out here. It will with a different set of example. Illustrates a binomial random variable of the order n equal to 10. So we have 10 values, 0 to 10 values. The first column gives value of k. We have k. The number of times that a Bernoulli event A can be counted in a trail. The second column gives the probability mass function for the parameter specified in the table. This is the mass function. For example, given the parameter in table 1.3, the probability of finding k equal to 4 will be just corresponding to here. You can see that it is 0.1460. Okay. The third column lists the cumulative sum for the PMF with the parameters given in the table 1.3. The probability of finding k equal to 4 or fewer events in A in the binomial trail of order n equal to 10 is this value, and this value is just here, right? For px less than or equal to 4 will be this, and this is nothing but the sum of all this. Okay, the sum of all this from 0 to 4, whatever is there. Okay, from 0 to 4, if you add all this, you'll get this, right? You'll get this. All this, if you add, you'll get this. Or one can say you add this with this, then also you'll get that. If you add this with this, then also you'll get this. Okay. So we are given some more examples of the same thing, whatever is mentioned there, right? So from that, we can try to plot the PDF and the CDF and write expressions for FY, Y, that is the PDF and the CDF. So PDF, how do we write? PDF, how do you write? We'll write here as 2.1 U minus, 2.1 del x minus 1, 3.2 del x minus, what is that? U x minus, del x minus 2, 4.8 del x minus 3 or y minus 3, because we are taking y over here, we need to write in terms of y, right? Then 5.4 u y minus 4, 6.9 u y minus 5. So all in terms of variable here is the independent variable here is y. Therefore, we should write in terms of y. So all this will have dels. This multiplied by del, this multiplied by del, this multiplied by del, this multiplied by del. And the argument for del here will be y minus 1, y minus 2 for the next one, y minus 3 for this, y minus 4 for this, y minus 5 for this. And here, these values will not be there, but rather these values will be there. But opposite to that, you write u in place of del, that's all. The expression for what you call the CDF will not be in terms of this. It will be again in terms of this only. Okay, in terms of this only, except that in place of del we will have u. Okay, we will have in place of the what you call impulse function, we'll have the unit what you call step function, unit step function. In place of unit impulse function, we'll have unit step function. Okay, so you can try to write the expression. It is just the same expression as we have written over here. Yes, we have written expression over here. Similar to that, we need to write the expression for those. Right. So plot also will be similar to that. So whatever is given here, same plot, similar plots will be there. Okay. Plot for this should be taken directly from the, third column. Plot for this should be taken directly from the second column. But when writing the expressions, it is only this, not this. Okay. Please remember that it is not this. Only this should be considered when we write the expression for both the PDF as well as the CDF. Do not get confused. Okay. So we can try to solve both these examples in the same way. Now let us go to the mixed random variables. Is it clear? If you have any doubts, uh, we can stop at this and then continue the next thing. But if you don't have doubts, we will continue. Okay, we'll continue. So next we come to the mixed random variables. A random variable that contains features of both continuous and discrete random variable is called a mixed random variable. So we'll have a combination. Mixed random variable uses techniques already developed for both the continuous as well as discrete random variables. Example we'll take here. Suppose a random variable x has a CDF shown in the figure 2.8a. So similar to this, right? So here the CDF illustrate is continuous at all values of x except at x equal to 2. At x equal to 2, it is discontinuous. You can see that it is discontinuous, right? CDF is discontinuous. Where there is a discontinuity of 0.2. Discontinuity of 0.2 means, from 0.4 to 0.6, there is a discontinuity of 0.2. The slope of the CDF is 1 by 5. So here it is 1 by 5 slope. The slope of CDF above this is 2 by 5, right? So it is, you can write this as, 1 by 5 into x. The value of fxx will be 1 by 5 into x, or x by 5 within the region 0 to 2. Then above the region 2, that is between 2 to 3, from 2 to 3, this value will be having the, what you call, x. This slope is 2 by 5. 2 by 5 into x. 2 by 5 into x, right? Between 2 and 3. Then later it will be constant. 2 by 5 into x plus, again, I should write the discontinuity also. 2 by 5 into x plus 0.5 in, 0.5, sorry, 2 by 5 into x plus 0.6 minus 0.4, that is 0.2. Okay, 0.2 should also be written. Might be, we will try to write it with the del x. Okay, so that's the way we have to write it. So therefore, therefore using 2.9, the PDF associated with this CDF is shown in the figure which is written there. Thus the area under the plot in the figure 2. What you call A to B, right? Area under the plot will be equal to 1. You will get this as 1. Minus infinity to infinity. So therefore here now I can just try to write here 0 to 2 is dx by 5. Integral 0 to 2 dx by 5 plus 0.2, that is the discontinuity, plus 2 to 3, integral 2 to 3, 2 dx by 5. This is 1 by 5 dx. This is 2 by 5 dx. So you integrate this, you will get 1.0. So this is the total probability that should give us the value 1.0 if you try to write this expression. So this is the process by which we should try to do all the numericals. So for us is given this another example, which is CDF is given as fxx equal to 0 between minus infinity to 0. This is CDF is given, and 7x by 30 plus 3 by 10 between 0 less than x less than 3. 1. 1 between 3 and infinity. So we need to find the probability density function PDF corresponding to this CDF. So let us take that example. I have not copied onto the PPT, so we'll go to the directly to the PDF. Okay. Now fxx we can is given to us, so we can plot that, right? So what is given to us there? If you just see, right, 0 between minus infinity to 0. So minus infinity to 0, 0. Then we have 7x by 30 plus 3 by 10 between 0 to 3. So 3 by 10 is the what you call intercept, right? And 7 by 30 is the slope. That is why it is written like this. 3 by 10 is the intercept, y-intercept, and 7 by 30 is the slope. And then later, afterwards, it is equal to 1. You can see that it is given as 1. It is given as 1 over here, right? Above 3. So this is what is plotted there. So that is what is plotted there, right? This is the CDF, cumulative distribution function. From this cumulative distribution function, we need to find the PDF. Now, how do you find that? Now, there is a discontinuity here at 0, right? So this continuity, this discontinuity will just give us the what you call this is just a line with slope which is 7 by 10. So 7 by 10 into x, if you differentiate that, you'll get 7 by 10. So that is why we have the constant over here. But because of the discontinuity, we will have the value, of impulse also here. Impulse also here. So this is because of the 3 by 10x. If you differentiate 3 by 10x, we'll get this value as, sorry, this is 7 by 10x. Because of that value, we have this, right? It is 7 by 10x. That is why 7 by 30, rather, 7 by 30. So I think this should have been 7 by 30, not 7 by 10, right? This should have been 7 by 30, not 7 by 10, right? Please change it to 7 by 30. So because 7 by 30x, if you differentiate, you'll get 7 by 30 only, not 7 by 10. Okay, here also you change it to the value 7 by 30. Okay, please change both these quantities to 7 by 30. Now this value is just corresponding to the discontinuity, which is 3 by 10, and that will be this value. Okay, that's how we can find. Now in the same way, we can try to solve the next numerical also here, right? Now here, if you see, it is 0 between minus infinity and minus 1. Okay, the plot will be a little different. Between minus infinity and minus 1, the variable here is y, not x. Here it is y. Here on the x-axis, you should write y. On the y-axis, you should write fyy. So it will be 0 between minus infinity to minus 1. Between minus 1 to 0, it will be this equation. Okay, so you need to separate this 3y by 10 plus 1 by 10. So 1 by 10 is the intercept at minus y equal to minus 1. 1 by 10 is the intercept at, what you call y equal to minus 1. And slope of the line starting at y equal to minus 1 will be 3 by 10. 3 by 10 will be the slope, which will go on increasing. So only difference here would be, if you compare this with that, if you compare this with, that there, okay. So here, you will have till minus 1, then discontinuity will be there here, and that discontinuity will be there of the value which corresponds to whatever is the constant, right? which is mentioned in the next group. And then after that constant, you'll have the slope again, right? Slope again, which corresponds to multiplication with a variable y, right? So intercept will be, 3 by 10. 3 by 10 also will be the slope here. So here it is different, here it is different. Then at y equal to 0 onwards, the value of fy will remain 1, right? That is, at means after y equal to 0, between 0 to infinity, fy will be equal to 1. So if you want a PDF, what you should do? Again, you need to, what you call, consider the,